So, we will be discussing about the crystal field theory for the octahedral complexes. Here, the diagram represents an octahedral geometry in which the central positive charge represents the metal and there are six ligands surrounding the metal atoms which are represented by the negative charge. As we know, the ligands used to approach along the axis rather than between the axes. So it is represented over here that diagram shows the along the z-axis the orbital is dz square and along the x and y axis the orbital is dx square minus y square. Okay, and now we have the five shapes and orientations of the 5d orbitals. As you all know, there are 5d orbitals which are represented as below. The lobes which lies along the axis are dx square minus y square and dz square. So that's the reason that they participate in the metal ligand bonding, because these are the only two lobes which are present along the axis and the ligands approach along the axis. And the next one are lobes lying between the axes, because they are present in between the two axes instead of being on the axis, right? As the ligand approach the metal ion, there is a repulsion between the ligand and the d orbitals. It means that whenever for forming an octahedral complex, there is a metal ion which would be encountering the ligands and the ligands would approach it, and there will be a repulsion between the ligands and the d orbitals, and thereby they increase the energy relative to that of the free ions. If the d orbitals were present in a spherically symmetrical crystal field, they could be represented as it is represented on the next page. I would definitely be showing it. So the mean value of the energy of these perturbed d orbitals is taken as 0, because the mean is always the 0 as the energy above and below to encounter them. Therefore, the mean value of this energy would be called as barycenter, at which the value would be 0. And however, dx square minus y square and dz square orbitals have lobes along the axis. Means I had already discussed about it that these two orbitals lie along the axis, so they point towards the ligands, right? Whenever there will be any ligands facing to, means there would be an electrostatic attraction between the metal and the ligand. They will encounter the metal from the along the axis, right? Whereas lobes of dxy, dxz and dyz, they lie between the axes as we have discussed earlier. So they lie between the ligands, because ligands are from the axis, not in between. So the next page is, see, as a result, the repulsion between ligand and dx square minus y square and dz square orbitals are greater than the repulsion between ligand and remaining 3d orbitals. It is point to be noted here, because it simply explains कि जो रिपल्शन होगा लिगेंड और डी एक्स स्क्वायर माइनस वाई स्क्वायर और डी जेड स्क्वायर लॉब के बीच में वो ज़्यादा होगा किससे, बिटवीन द लिगेंड्स के बीच से एंड द रिमेनिंग 3d ऑर्बिटल्स, और जो बाकी बचे हुए 3d के ऑर्बिटल्स हैं उनसे. कंसिक्वेंटली जो एनर्जी है डी एक्स वाई डी वाई जेड एंड डी एक्स जेड orbitals are lower than those of dx square and dz square. Yeah, it would be obviously because the ligands are forming some instability, due to which the energy of dx square minus y square and dz square are high relative to the other three energies of dxy, dyz and dxz, right? So the later two of high energy are called Eg, means dx square minus y square and dz square will be represented by the Eg, and dxy, dyz, dxz will be represented by the T2g. And the energy gap between Eg and T2g would be delta O. Delta O is represented or named as crystal field splitting energy or crystal field stabilizing energy. It is usually represented by delta O, and you can see here the barycenter, which has the value of 0. Earlier there was d orbital in the free ion state in which degenerate 5d orbitals were present, and suddenly when the ligand approaches the metal, and the average energy of d orbitals in the spherical crystal rises up, and finally in the presence of ligands it splits into the two parts, dxy divisor dxz, with lower energy because ligands do not interact with them as they are between the axes, and the orbital dx square minus y square and dz square are present on the axis, so the ligands would have a repulsion between them, and due to which its energy is increased. So the dx square minus y square and dz square are of higher energy. Now we will compare the energy with respect to barycenter, and the lower part would be having the energy of minus 0.40 delta naught. It means each dxy, dyz, dxz would be having energy with the electron multiplied with minus 0.4 delta naught, and the above energy would be 0.6 delta naught, right? For example, we have one electron in dxy. So to calculate the CFSE, we would definitely multiply the one electron by minus 0.40. So it would be the crystal field stability splitting energy. Thank you.